Hello, everyone, and thank you for joining us for today's e-showcase, MABR at Work, Technology, Evaluation, Design, and Construction of the Full-Scale MABR System at the Hespeler Wastewater Treatment Plant. Today's e-showcase is sponsored by Suez, and thank you for sponsoring today's event. I have the pleasure of introducing today's presenters, Jeff Peters and Olaf Nativ. Jeff Peters is a water industry professional with 20-plus years of experience in the application and commercialization of innovative technologies. Jeff has a strong technical foundation in water and wastewater process design combined with commercial acumen. Olaf Nativ has been in the water and wastewater treatment industry for over 25 years. He currently is a senior process engineer for Stantec, where he provides process wastewater design for municipal, industrial clients throughout North America. And now I will hand the presentation over to Jeff and Olaf.
Thanks, Regina. Welcome, everyone. Thanks for attending. Olaf and I are going to share a story with you today about a technology that's gaining a lot of traction in the wastewater market. And it's a story that actually starts back in the 1960s when researchers had this spark of an idea of using a membrane to transfer oxygen into a wastewater treatment system without the use of bubbles. And the reason they were interested in this was to see if they could change this paradigm of the energy that's required for wastewater treatment. And like most ideas, most early ideas, it faced many technical challenges in the beginning. And it took several decades of other researchers exploring this idea to optimize the process and look at new applications of the technology to see if we could solve other problems apart from just this energy paradigm. Meanwhile, the market evolved as well. And we've had increased urbanization, the introduction of nutrient removal requirements, and it's forced us as an industry to challenge the conventional solutions that we've had for wastewater treatment. And if we think about the current situation that we're in, this change and this need is accelerating even further as we face the need for attention to sustainability, whether that's further reduction of energy or greenhouse gas emissions, and also resilience to the realities of climate change. And that brings us to today. And the exciting thing about MABR technology, which is what we're going to be speaking of today, is the fact that it takes this spark of an idea that was back in the 1960s to solve what's an old problem, wastewater treatment, in a new way, and in a way that addresses these challenges that we're facing. And the Hespeler case study, which Olaf is going to introduce us to at the second half of the presentation here, is a great example of the manifestation of this idea into practice. So the agenda for today is I'm going to give an overview of MABR technology, and then I'm going to pass to Olaf, and he's going to introduce the case study of the Hespeler plant, which is a full-scale implementation of MABR technology. We're going to leave approximately 10 minutes at the end to do Q&A. So we'll hold all the questions until the end. I encourage you to use the chat function. So you'll see on the bottom right of the screen, there's a link to a chat window, and you're welcome to pose your questions throughout the discussion, and we'll curate those at the end. I also encourage you to use that as a way to engage with the rest of the attendees here or the other panelists. And I may even use it myself to ask you some questions as we run through the content here. So let's begin with an overview of MABR technology. So Z-Lung is the MABR product that's manufactured by Suez. And the way I like to think about MABR technology is that it has four primary values. The first has to do with process intensification, which could mean doing more work in an existing tank volume. So that could be increasing plant capacity. That could mean increasing the degree of nutrient removal without having to build new tankage. So the core value proposition is exchanging the conventional approach of building big concrete tanks for putting technology into existing tanks and squeezing more out of existing assets. In addition, we have resilience. So MABR is an attached growth process, which is generally understood to be more resilient to process upset and changes in operating conditions. Simplicity in terms of being able to execute an upgrade by adding mechanical equipment into an existing tank rather than a large, complex civil construction project. And I would say the gravy on top of all this is the energy savings, and considerable energy savings up to 50% relative to other solutions. So the way we've been applying MABR technology is to solve problems related to capacity increase, augmenting ammonia removal, improving or implementing nitrogen removal, and improving or implementing biological phosphorus removal. And I'd like to, we've got a good number of attendees here today, and I'd like to hear from you if you see plants that face these needs. So is there a plant that you're aware of? Either it's one that's within your own facility or your own portfolio of plants, or it could be a client that you're working with who has a need related to an existing activated sludge plant that needs to expand capacity or improve nutrient removal. And I'd appreciate it if you do, just into the chat function, perhaps just type need, and then perhaps also add some color to that, whether it's a need for capacity expansion or it's a need for nutrient removal or something else. So feel free to add that into the chat as we carry along here. So let's look at how MABR technology works. The basic premise is we have a biomass carrier that we insert into an activated sludge system, and we grow biomass on that carrier or that media. And because we can increase then the inventory of biomass in the system, it means that we can do more work without having to increase tank volume or increase mixed liquor concentration. So that premise or that principle is very similar to IFAS, which has been around for decades. The distinction and the unique feature about an MABR is the fact that this carrier material also breathes, if you will. And what I mean by that is it's a medium for the transfer of molecular oxygen. So we can transfer oxygen to that biofilm without the use of bubbles, which allows us to change the game in energy consumption for oxygen transfer. And it also introduces some unique properties that have process advantages that we'll describe further. Z-Lung or MABR is not a filter. We talk about a membrane, but not a membrane in the context of solid-liquid separation. There is no solid-liquid separation. It's a membrane for the transfer of oxygen. It's also not a fine bubble diffuser. So we're going to talk about diffusion, but I'm speaking in terms of molecular diffusion, not about diffusion of fine bubbles. In fact, there are no bubbles in this process. So if we look in closely and schematically, if you can imagine a hollow fiber membrane, and from the top of that membrane, we deliver air with 21% oxygen. The membrane material that we select has properties for the diffusion of oxygen. So if we have a concentration gradient of oxygen from one side to the other, molecular O2 will diffuse through that material. And what happens then is we grow a biofilm on the outside of that membrane that's performing the treatment. And the oxygen required for that treatment is being delivered by the media itself. So the simple image you see on the right here would show the oxygen inside the lumen transferring through the wall and providing aerobic conditions to a biofilm. And in those aerobic conditions in the biofilm, we can perform nitrification. And the primary purpose of the biofilm in an MABR for the applications that we're speaking about today are for getting more nitrification in a small volume. So it's not intended to oxygenate the entire tank. It's really intended to oxygenate the biofilm. So we have the ammonia and the COD entering the biofilm from the one side and the oxygen entering from the other side, which has some certain magical properties that I'll describe in a bit. Just to give you an idea of what this looks like physically, this is an image of what the technology would look like as it is scaled up. This is 1 millimeter diameter approximately. We start with a reinforcing core. That's the small dark circles that you see in the middle, which is like a polyester reinforcement, which provides a structural backbone. And then we orient a series of hollow fiber filaments, which is the membrane material itself, that are about the diameter of your hair around that reinforcement. We send air down the length of each of those gas transfer membranes. Oxygen diffuses out and supports the growth of a biofilm on the outside, which is where the biological treatment is occurring. So we take these filaments, we put them on what we call a cord, which is the reinforced structure. We pot them into a top and bottom collection header that we call a module. And we take a series of modules and put them into a cassette frame, which is nothing more than a stainless steel housing to support cassettes and allow a reduced number of system connections. We send air to the cassette. The air enters the lumen of the membrane. Oxygen diffuses to the biofilm. And we take the exhaust gas, what remains, and we use that to mix the system. These cassettes then are installed directly into the activated sludge system. This is a picture from a plant in the UK where you can see the cassette being installed into the anoxic tank. Typically, the cassettes are installed in the anoxic tank because that allows you to achieve simultaneous nitrification and denitrification. where we have nitrification in the biofilm and denitrification happening in the suspended biomass around the biofilm, which is an additional process advantage. So let's talk about those advantages. The first was process intensification. So the simplest way to think about that is I have more bacteria inventory in my system, which means I can do more work. But in fact, there's additional advantages. If you think about a traditional attached growth system like IFAS, it operates in what we call a co-current diffusion mode. That means the oxygen and the pollutants, the BOD and the ammonia, enter the biofilm from the same side. And that creates this competition for the oxygen between the heterotrophs, the bacteria that want to oxidize the COD, and the autotrophs, the bacteria that want to metabolize the ammonia. And because the heterotrophs are fast, they tend to dominate in this environment. And the bulk of the bacteria in a biofilm like this would be the heterotrophs. And MABR changes that paradigm. We operate in what we call countercurrent diffusion. Oxygen entering from one side and the BOD and the ammonia from the other. So for the BOD or the ammonia to reach the oxygen, first it needs to diffuse through the thickness of the biofilm to reach that oxygen. And ammonia is a small molecule relative to a large molecular weight organic, so it has a competitive advantage to reach the oxygen. And because of that, when we sample the biofilm in an MABR, we find that it could be up to 10 times higher in proportion of nitrifiers than a conventional system. And that's important because in the context of a plant where you're looking to intensify nitrification or nutrient removal, it tends to be the nitrifiers that are your process bottleneck. So being able to intensify the nitrifiers is very important. Resilience comes from the fact this is an attached growth process. Because the bugs are stuck in the system, they're attached to the media, they're not going to get washed out in a peak flow event. We've also seen the very rapid response to the bacteria in changes in diurnal flows and loads, for instance, and stable cold temperature performance because we're not reliant on the growth kinetics of the nitrifiers because they're stuck in the system. And here's an example of the simplicity. This is a plant in Belgium where we installed the cassettes without dewatering the tank. So this idea is, again, can we exchange the need for big, complex civil construction projects and instead be able to install the technology directly into the activated sludge tank, even potentially without having to dewater the tanks. And the gravy on this is the energy savings. So here you see the energy efficiency or the aeration efficiency of different aeration options. So a fine bulb diffuser, once it's put into mixed liquor and you account for the alpha factor, might deliver 1 to 2 kilograms of oxygen per kilowatt hour. Whereas with an MABR, without the fine bubbles, without bubbles at all, and the transfer of molecular oxygen, we can get up to 6 kilograms of oxygen per kilowatt hour. In addition, there's the potential to have some ancillary benefits. For instance, if we have simultaneous nitrification and denitrification, we may be able to eliminate or reduce the nitrate recycle pumping requirements. And I also like to think about the sustainability of the technology, and I reflect on sustainability in a couple of ways. Firstly, making better use of existing assets and avoiding the construction of new concrete tanks, which occupy space and have a GHG impact. Improving nutrient removal, which has a positive impact onto receiving water bodies. Reducing greenhouse gas emissions in terms of energy and N2O, and avoiding plastic pollution. So, one way to think about an MABR is it's like other intensification solutions, except it overcomes some of the challenges of those intensification solutions. So I'm going to pose another question to the panel here, not the panel, but the participants, and say, do you, when you look at technology options or evaluation, do you consider sustainability in your evaluation? Used to be that capital cost and OpEx was all we considered. Is sustainability something that's on your radar? If so, give me a yes, and perhaps tell me what sustainability means to you. Is it energy? Is it greenhouse gas emissions? Your feedback there would be greatly appreciated. So MABR technology, or the Zilong product, has been commercialized for about 5 years, and we now have 12 plants that are in operation or design or construction. And in that 5-year period of time, we've done more than 30 technology demonstrations. So in that short period of time, there's been a real rapid evolution of the technology and commercial adoption of the technology. And the project we're going to highlight today is the Hespeler plant, which is a great example of taking all the learnings we've had and applying them in practice for a full-scale implementation. So I'm going to pass now to Olav, and he's going to share that with us. Olav.
Thank you, Jeff. Let's advance the slide here. There we go. So welcome. The subject of my presentation today is the MABR integration at the Hespeler Wastewater Treatment Plant. The plant is located in the region of Waterloo, which is approximately an hour drive west of the city of Toronto. In terms of geography, it's at about 43 degrees north latitude. It experiences climate-wise a warm summer, but a cold traditional Canadian winter, you might say, where we see wastewater temps drop down to 10, 12 C. And in this particular case, this plant struggles and it loses nitrification when they see those low winter temperatures. When Stantec got involved with the project, the site looks, as you see on the aerial view, it had essentially been a plant that had been somewhat neglected for quite some time. And the main reason being was that the region really wasn't certain what the long-term future for the site was. It wasn't until a master plan was completed, which really identified the need for this facility in the longer term. And having done that, the region decided to essentially do a condition assessment as well as a process review to really identify those things that needed to be addressed immediately to basically sustain the site going forward. So coming out of that review, the key items that were identified that needed upgrade were essentially a new headworks, as the existing facility had nothing essentially for headworks, with short secondary clarifier area, so we needed to add some area. It didn't have any real sludge thickening or any on-site proper stabilization, so there was upgrades to thicken the WAS as well as to improve the on-site digestion. And then there was also a modification to allow peracetic acid disinfection on site, the result of extensive study with the provincial regulator. And then ultimately, MABR sort of fell into place because of an ongoing study to look at the future implications of nitrification for the site, which will be the subject of today's discussion. So, next slide. Just briefly, just to try to understand the sort of the sequence of design and construction and how we came to have MABR on site, I'll just quickly go through the sequence of events, essentially. So the region was fortunate. They received some higher level grant funding money, which essentially forced the early design and tendering of a third secondary clarifier, and that had to happen right away just to respect the grant funding timelines. So that was issued as contract one. Now, while contract one was in construction, Stantec looked at the other aspects of the plant upgrade and started design of those elements. And coming out of that, in that design, we essentially designed a new headworks, and that involved new 2mm drum screens, as well as vortex grit tanks, some space for admin. The other key element was the new WAS thickener process. In this case, an ultrafiltration membrane system was selected, basically taking the WAS, batch thickening it to 4%, and then transferring the thickened WAS into the former aerated sludge holding tanks, because we were reducing the hydraulic loading rate onto the aerated sludge holding tanks. We could essentially get sufficient sludge age to properly stabilize the solids and do all the proper on-site stabilization, which was one of the key requirements, and in doing so also reducing the trucking off-site tremendously. Some other minor changes that had to be made were affecting the blowers. That design package essentially was completed, was then tendered as contract 2. And while contract 2 was underway, should also back up a little bit, while in design in phase 2, the region was interested to plan for the future nitrification for the site. As it was, the plant didn't have to nitrify, but when this plant needs to be expanded, which wasn't this phase of work, this is just to deal with the current deficiencies and basically bring it up to its current capacity. But going the next future expansion, there was a recognition that the traditional expansion would be building a lot more tanks at significant cost to allow for the winter nitrification. MABR was a new novel technology that was out there, and the region essentially requested us to look at that. And in the early feasibility study, it showed real promise. The region decided then to design flexibility into the contract 2 so that MABR could be added at a later date. It wasn't really certain when it may happen, may not happen at all in this construction. It may happen when the plant expands. But as it turned out, while contract 2 was tendered and out in construction, the region went out and requested some funding, and at the same time advanced the MABR design to get a better idea of what it would look like on site, conceptual design, better improvement costs. And then first round of funding essentially failed. Second round of funding request was successful. And when the money came in, the decision was basically to add that the MABR to the contract 2 as a change order. So that's where we are today. If the money hadn't come in, this MABR wouldn't happen today. It might have happened 10 years from now. Let's say when the plant expanded, things may have changed. But that's where that's the result of what happened essentially. So what were the drivers for MABR at Hespeler? As I noted earlier, the region knew they were faced with having to expand this plant in the future just for growth, but also for nitrification. And so they wanted to crystal ball and look at how this site might be expanded for future nitrification. So the assumption would be the plant would be expanded 50% for growth, and at the same time we would have to achieve nitrification. So in the left box, essentially, to get the nitrification, you end up having to build a lot more bioreactor tankage to be able to achieve, maintain the nitrifiers in the system in the winter when the temperatures drop to 10, 12 C. Versus on the right, an MABR integration possibility. And this was assuming we built new purpose-built tanks today to hold the cassettes in front of the aeration tanks. And because we can increase the nitrifier mass, they're fixed on the film, we could essentially do the winter nitrification that we needed. And when you compare those two options, certainly construction-wise, there's a clear winner. The MABR project is roughly half the cost of what it would have been as its traditional tank expansion, following the same philosophy that was on site. And obviously, from the footprint perspective, it's clear we could keep it within the existing fence line. There's sensitive environmental lands around there, so that was a real benefit to the region. And also some of the other factors, there's a real energy saving by implementing MABR versus nitrifying into your larger aeration tanks. And also, I should note, it's not just the technical financial that was driving this, it's the people aspect. And it so happened that we had to, consult with the regulator. They were on board. They were willing to approve the implementation of MABR. The region had technical folks involved that certainly, without their involvement, would not have seen this happen. They could see the real benefit to this. and also the contract operator, Aqua. They also were willing to work with the team. And without those players around the table, this would never have happened as well. The Hespeler MABR design basis. So it's the traditional things. And I see I'm going to have to probably speed up a little bit. But the key decision was made: do we put the membrane cassettes into the existing tanks, or to put them into purpose-built tanks in footprint before the aeration tanks? The decision was, in developing contract 2 drawings, is provide the flexibility initially that they could go both ways. But when it came time to actually truly pre-select this, the decision had to be made: we're going to put them in purpose-built tanks. We have space, we've got the hydraulics to allow it to happen, and the construction staging would be fairly simple to do as well. It's a separate space and time. Obviously the vendors needed to know design basis flows and loadings. We gave them that, as well as what the effluent ammonia targets would be. And in doing some high-level modeling, basically what we determined: if we have purpose-built tanks, the TKN comes in. When it leaves the tanks, it needs to be approximately 12 milligrams per liter or less, such that when the flow passes through the downstream aeration tank in the wintertime, we'll be down less than 7 milligrams per liter to achieve a future ammonia limit that was established through a receiver study. And they had to do it in the worst case situation, where the downstream mixed liquor was non-nitrifying in a washout situation, so running a low sludge age. So the whole system essentially relies on sufficient nitrification on the film, plus the slough that passes into the mixed liquor, such that we can achieve our final effluent goal. So coming out of our design, what you see there is a 3D rendering of what we have on site right now. I'll just briefly discuss what we have. We essentially have an inlet valve chamber where all the screens, raw sewage, as well as the RAS, pass through, and through valving, we have the flexibility to pass flows either into the MABR process or bypass through piping underneath directly into the aeration tank. Normal mode of operation is essentially all the screen sewage and all the RAS passing into an influent splitter box where it's fully mixed, and then partitioned through basically inlet gate valves, and passes through one of 4 trains, and then it overflows a weir, drops into an effluent box, and then through a pipe connection continues on to the aeration tank. So as it is right now, each tank has 9 cassettes, and we have 2 blank spots for future additions, and also to provide some flexibility to see how this all works out. Looking at some of the unique aspects of the MABR here, as I noted before, the business case. When you look at the MABR in purpose-built tanks versus an expansion for nitrification, significantly less costly. And that was certainly a very important consideration to the region. And then when you factor in that the actual MABR process that was installed here wasn't for the future expansion, but to address current permit of 9.3 MLD, this process is in fact much less expensive than the future expansion. In terms of scale, as it is right now, I understand it's the largest MABR plant in the world in terms of cassettes. There's 36 cassettes being installed. And in terms of process design, really the main driver here is to get winter nitrification. When we have an activated sludge that is in a nitrifier washout condition and normally wouldn't be able to real significant ammonia removal. We're now relying on this cassettes to do the work. And so that's this key function. The implementation here, we decided to go with purpose-built tanks, really to minimize disruption during construction. And it also allows for great isolation of the process to be able to observe what's happening in future testing. So that certainly has some benefits. Procurement, this was competitively bid. There was 2 vendors that submitted tenders. They were evaluated, and ultimately Suez was selected. Some of the interesting design considerations here. Because we're doing the full plant, we had to consider the head loss. We had essentially the headworks elevation here, the aeration tank elevation here, and we had to make the structure fit within the hydraulic grade line constraint. So that was a key issue. We also have some flexibility to deal with mixing. This concept relies on the cassette being tight to the walls and the cassette providing the internal mixing of the mixed liquor as it passes through the cassettes. That is something that we're going to be interested to see. There is flexibility here to actually lift the cassettes if we have to provide supplemental mixing underneath. Testing flexibility, as I mentioned before, there's lots of flexibility to allow for different flow routing of screened sewage through the MABR, bypassing the MABR as well as the RAS. We also have some online instrumentation to be able to monitor more closely the ammonia removal. And we have provisions for future expansion, either add more cassettes to the blank zones. And I understand they're also working on cassettes with higher membrane area density. So there may be ways of actually replacing cassettes with higher area density cassettes to achieve more capacity that way, as well as space to add more trains alongside the existing trains. In plan view, this is pretty busy, and I'm going to have to go a little bit fast, but it's essentially the same thing as the 3D rendering that you just saw. We have the valve chamber here, raw sewage and RAS enters here. Normally it passes into the inlet chamber, where we also have a jet mixing pump to provide additional mixing here, passes through gates individual to each train, flows down the length of the MABR tank over the effluent weir into a box, underground pipe into the aeration tank. We also have a couple of blowers, small horsepower blowers, do standby to provide the air that the cassettes require. Moving on. In section view, one of the things there's space on the site is we put a lot of piping underneath the base slab of the MABR, and we had the hydraulic grate to allow us to do that as well. And essentially flow comes into the in-splitter box, through the gate, through the empty blanks, through the cassettes, over the weir, and down back onto the aeration tank. The walls have been elevated or extended another 600 millimeters to provide additional flexibility if we have to lift the cassettes. And finally, getting close to my end here, where are we with the project? Construction is planned to be complete Q3 of this year. The concrete tanks are essentially complete. This is a picture of the tanks here a month ago, showing the 4 passes with the influent splitter box. It's up tight against the membrane thickener building. All the piping underneath to preserve space. Room to add trains to the side. The startup commissioning, assuming construction done Q3, there will be a biomass acclimatization period in Q4. And basically, it's to begin the growing of the biomass to ready the process for performance testing. And we're targeting Q1 of next year, basically 6-week monitoring sampling period during the coldest operating period of the year, where we'll be down around 10, 12C, when it's really the most challenging period of operation. And really, we hope to basically reduce the mixed liquor sludge age down to 3 days and basically wash the nitrifiers out. So that essentially the test is going to be seeing how much of the ammonia we can remove using the fixed film of the MABR. And in fact, that's one of the important things here to note. The plant doesn't have to meet an ammonia limit right now. So in terms of testing, we got lots of flexibility and we're not risking any compliance as it is right now. So it's really a super time to be testing this process. And I'm really excited about this. You know, once the performance test is passed, and that's going to be key. The region has also partnered with academic institutions for NSERC study, and they're really going to put the process through a significant study to learn more about this. And obviously, once it's up and running, we're going to learn more, and we're going to be in a position to be able to bring that information to the broader industry. So with that, I'll say thank you, and I'll pass it over, I think, to Jeff, or maybe it's Regina.
Thanks, Olaf. So we've got about 10 minutes here to do some Q&A. Thank you for the questions that you've been putting into the chat. You can keep doing so. What I'm going to do is curate them and see if I can group them together so we can answer as many as possible. So there were a couple of questions related to considerations for the life of the product and how it evolves over time with respect to fouling or what the performance impact over time is. So I'll take that one. So this is very different from an MBR in the context of an ultrafiltration or an MBR membrane where a biofilm is a bad thing. And in the case of an MABR, we want the biofilm because it's the biofilm that's doing the treatment. And the key is to control the thickness of the biofilm, because if it's too thin, you don't have enough bacteria to do the work. If it's too thick, you have too much resistance to diffusion of the oxygen or the substrate. So the way we manage that thickness is by using a coarse bubble aeration system. So once the gas is past the membrane, we take what's left and we use that and introduce that to a coarse bubble aeration grid under the cassette that provides mixing energy to renew the substrate and to control the thickness of the biofilm. And that's how we slough off the excess biofilm and control the thickness. So in our experience, the longest running plant is 4 years at the Yorkville Bristol Sanitary District, and we've seen no degradation in oxygen transfer efficiency. And we anticipate the life of the product will be 20 years. There were some other questions, Olav, around mixing and clarification on mixing. So I'll start, and then you can talk about the specifics at Hespeler. So that coarse bubble mixing that I described provides enough energy to mix the control volume of the cassette. If we're putting cassettes into an existing activated sludge tank that might be deeper or wider, then it's typical that you would need some supplemental mixing to make sure the rest of the tank remains in suspension and you don't have settling. In the case of Hespeler, where the decision was to make purpose-built tanks, it was a bit of a different approach, right, Olaf?
Yeah, sure. I mean, basically, the cassettes, there's very little clearance between the walls and the bottom of the cassettes. It's in the order, I think, of 100 millimeters. So it's essentially tight. And it does rely on the internal mixing of the cassette itself to provide sufficient mixing. And in my mind, that's a bit of a question mark. And so we and frankly on the region's part as well. So that was why the decision was made to provide flexibility to lift the cassettes. And obviously, we're hoping that that's not required.
And we've got another question on Hespeler, Olav, which I think is important because of this consideration for the value. You mentioned that when you compared the costs to a conventional approach, which was building new tanks, the CapEx, I believe, was about half of the conventional approach. So is that specific to the Hespeler situation, would you say? Like, was there anything unique about the construction conditions for new tanks, or could you?
Maybe one thing, like in the case of Hespeler, their existing tank volume was very small, which meant you had to build, relatively speaking, more tank volume to get it to nitrify. So that kind of, was a disadvantage to the traditional tank expansion versus normal, let's say. But I think in most cases, the and again, it also depends a little bit on what the effluent targets you're trying to achieve. If you're trying to achieve very stringent effluent ammonia in the winter, MABR may struggle in that you have to put a lot of cassettes in, and then maybe it's not as cost effective. In this particular case, the plant only has to achieve a wintertime nitrification of 7 as compliance, and for objective of 5. And then that allows you to that makes it maybe allows you to need fewer cassettes than, let's say, if you had a permit requirement down to 2. So every case is a little bit different.
Yeah, I'd expand on that also, because in the context of a cold temperature application, which drives higher SRTs to achieve nitrification, one of the benefits of MABR is that it allows you to design and operate your aerobic SRT at a lower value, because you're getting nitrification in the biofilm and you're seeding the nitrifiers into the aerobic tank. So when you have these cold temperature conditions or cold temperature plants, they can have an advantage because of the large SRTs that drive big tanks for conventional systems.
Exactly, that's exactly it. In this case, we're going to be running the winter sludge age at 3, 4, 5 days, and the mixed liquor won't nitrify at that temperature. We're relying on the MABR nitrifiers to do the job.
Let's switch gears a bit here. There were some questions around maintenance. I'll tell you my perspective, and then Olaf can share what specifically has been considered for Hespeler. This is very different from, again, an MBR or a UF membrane, where the intent is not to chemically clean them. There is no chemical cleanings because we don't want to destroy the biofilm. It's more like a fine bowl diffuser where it goes in the tank and is left. So our intent is that every year we pull 1 or 2 of the cassettes as a sample, so to speak, just to check the mechanical condition of the nuts and bolts. But apart from that, we wouldn't be removing these cassettes on a regular basis. And for that reason, you'll see at Hespeler, there is no permanent overhead crane, which you might see more commonly on an MBR plant, because the cassettes won't be removed on a regular basis. Right, Olaf?
That is the current plan, yes. I know that we discussed, the possibility to add some lifting mechanism to do spot checks, let's say. But like most projects, the budget gets tight, and you have to make a decision on what you can afford or not. So in this case, the plan is that they'll have to get a boom truck in to pull.
There was another question on phosphorus removal. We've been speaking primarily about ammonia and nitrogen removal here, but the technology is applicable for phosphorus removal. The first plant we have in North America, the Yorkville plant, which we presented on before, was actually part of the motivation for that plant was to implement biological phosphorus removal, where the idea was not to do the biological phosphorus removal in the biofilm, but to intensify the nitrification piece so that you could create space to do an anaerobic zone to do biological phosphorus removal. Equally, you could add chemical to do chemical phosphorus removal. And the question, I believe, was, can you get down to 0.03 milligram per liter of phosphorus? Well, you could, but you'd need some effluent polishing to get the solids out. And I think, time for one more question, which is quite interesting, one I'm passionate about, which is greenhouse gas emissions. So the ability of the technology to address greenhouse gas emissions comes from 2 places. First is the energy savings, of course. But the second one that's really interesting is the ability to reduce N2O emissions. So it's well understood that N2O is a powerful greenhouse gas, 300 times more powerful than CO2. And there's some evidence that suggests that N2O is produced as an intermediate in the nitrification and denitrification process. And MABR has some advantages to reduce that because of the special conditions in the biofilm, and mitigate it by collecting any N2O that's produced. So if that's something that you're interested in learning more about, you can follow up with me. I think we'll close here. I just want to thank you for attending and your patience. I understand there were some issues with getting on. I appreciate those of you that stuck around and persevered. The one thing I want you to take away from this is if you come across a plant that needs an upgrade for capacity expansion or nutrient removal, you can think about MABR as a new tool that's at your fingertips to solve the problem in a different way. Rather than building new concrete tanks and consuming more energy, think about MABR as an intensification approach to solve the problem in the existing tanks and position the plant for the needs of the future. So thanks again. With that, I'll pass to Regina here to wrap us up.
All right, thank you. This was great. Thank you, Jeff and Olaf, for your presentation, and to Suez for sponsoring today's event. This actually concludes today's e-showcase. Thank you for attending. The recording will be available at buyersguide.web.org. We will send all registrants an email tomorrow with this link, and please visit our event calendar to sign up for future webcasts.
Thank you.
Thanks.